by this silly story about people trying to walk over, every bridge in a city. But so I was trying to think about. Interesting. I remember there's definitely some more practical applications of this. Yeah, so for example, there's something called a, this is kind of an aside. This is like an application, which I just find interesting. There's something called a de Brown, probably not pronouncing that quite right, a de Brown sequence. It's what is it? It's a sequence of ones and zeros that includes every possible string of k bits as a substring. So for example, let's see if we can do it for, like even just for two, like 1, 1, 0, So if we think of it in a cycle, right? Then like here's 1, 1, right? Here's 1, 0, here's 0, 0, and here's 0, 1, and that's every possible sequence of 2 bits, but kind of compressed into this, just this string of 4 bits. So all oops. Looking at it here, it's like, well, I keep getting it wrong. And they can overlap, but as long as kind of like every sequence occurs in there somewhere. And why would you want this? Well, there's ways that like, if you need to like try out every possible sequence of bits, this gives you kind of a more efficient way to do it. So you don't have to like regenerate the whole thing from scratch every time. Each thing you just go to the next bit and you throw away the oldest bit and you've now got your new sequence. There's other kinds of there's things that this is used for. And the question is, how would you come up with something like this? Well, if we think about a graph, so the graph with vertices, can I find an Eulerian circuit in this graph? An Eulerian circuit in this graph, right? Because every time I go across an edge, if I follow another path, it means that those are kind of compatible. Like if I go across this edge 1, 1, 0, and then I follow this edge 1, 0, 1, it means that this thing starts with 0, 1, 0, and this thing ended with 1, 0. So I can put them right kind of overlapping in a string. So if I can find a path through this entire graph that goes on every edge, I'm going to have my string of bits that will be a de Bruijn sequence for 3 bits, right? Here was a de Bruijn sequence for 2 bits. I don't know, is there an Eulerian circuit or path in this graph? What do you all think?
I feel like there's going to be a signal direction where like we're not going to be able to like run through the possibilities.
Yeah, but if we're just trying to, if we wanted to prove that there isn't one, that might be harder, right? Well, then we need some kind of theorem that tells us whether, like, how we can know if it's possible. If there is one, we could just try some things, and if we find it, then we found one, right? So, I think there is one, which is why I'm asking. Like, I think there's supposed to be one, but I'm not sure. Let's just try something. So, like, let's start here. So if I start here, I can go this way, right? And now I have 2 choices. I could go down here, or I could go like across this diagonal. I think either way is fine. So if I can go down here and then back up here, and then I can go across this diagonal, right? Over here, and back there on the group. It works. So that would correspond to, we can read off the bits now. So 1, 1, 0, 1, 0, 0, 1, another 1, another 1. Oh, well, these 2 ones actually are the same as the beginning ones. So yeah, that's it. So if you look at this, like if we look at all the, there's 1, 1, 0, there's 1, 0, 1, 0, 1, 0, 1, 0, like every possible string of 3 bits should be in there somewhere if you wrap it up. 0, 1, 0, 1, 1, and 1, 1, 1, 1. Anyway, it's just a little interesting aside. So this is one application of the idea of Eulerian paths. So let's, I'm going to make some graphs here, because we have been talking about stuff last time, but I want to figure out kind of what is the theorem that we want to prove. I'm going to make some example graphs, and you tell me whether you think they have an Eulerian. Let's just think about Eulerian circuits right now. Turns out once we can figure out the right thing to say for Eulerian circuits, then paths in general are not too much harder. So you can start thinking about those while I'm drawing the graph. What do y'all think? Does this first graph have an Eulerian circuit? Eulerian circuit, I have to and then be able to come back to the place where I started. Yeah? So yeah, this one does, right? I can just like go in here. And so it's no problem visiting the same vertex twice. That's okay. I just can't use the same edge twice, so do that. So check. Right? What about this one? Think it does? How does it?
Well, I'm just doing the thing where I'm kind of breaking it down into pieces and shapes.
Okay.
And so I see it's a triangle, and I know each triangle is going to do a circle.
That's true. So each triangle by itself, I can like go around a circuit, right? But I can't reuse edges. So like I can't do this triangle and then also do this triangle like this because I would be using this edge twice. Right? Yeah, I mean like this one, you really can think of breaking it down into these two triangles and then putting them together. This one we can't quite break it down into 4 triangles because they share edges, so they're not like independent of each other. So let me remind you what we were talking about last time. That'll help us here. So remember that if we look at a single vertex, that has some number of edges coming out of it, when we visit it on a path, and especially if we're looking for a circuit, like our path kind of has to, it doesn't really matter if it's the start vertex or vertex in the middle. There's actually no difference. It's just a loop that goes through all the edges. So every vertex the path goes through, I'm going to use up like 2 edges when I go through there.
So are you saying that second one doesn't then?
Well, why not? Can you explain why not? So you're right, it doesn't.
Well, I can't explain why it doesn't, but if I can't explain why it does.
Okay.
But I feel like other than sharing the edges, isn't that enough to even like not?
Not necessarily, because maybe we're just not clever enough. Maybe there's a different way to think of it, or we could do it. Even just because like breaking it down into triangles doesn't work, that doesn't mean like there might be some other way that doesn't work. Yeah.
Because you just draw one triangle out of it, like you just draw one triangle going to the middle of that. But regardless, you have left the top and the bottom with a like they're going to get stuck out.
Angling, yeah.
And so you can only choose one of those. And maybe if you get one of the edges, you could try to do it. But I imagine there's still more problems you can go along
Right.
that way.
Well, and remember, so for now, for today, we're only thinking about circuits. So I definitely want to start and end at the same place. It turns out if we can just answer that question of like when there's going to be a circuit or not, extending it to talk about when there's going to be a path turns out to be very easy. It just makes our lives simpler than the whole thing. So yeah, I mean like, just think about like, let's say I had a path that goes through here, right? Because this vertex has degree 3, when I go through there, I've used up 2 edges, and now there's only 1 edge left for that vertex, and that's no good, right? Because if I ever come there, I'm going to get stuck. And I can't get stuck because I want a circuit. I can't like start somewhere and end up somewhere else. I have to be able to keep going. So, right, this is bad. Okay, so based on that, can anyone make a conjecture about like what's one way we can tell for sure that a graph does not have an Eulerian circuit? What do you think?
Any vertex has the odd.
Okay, you're saying if any vertex has an odd degree? Okay, what do y'all think? So,
Maybe multiple would be a way to do it, but no, you have to be any.
right, so certainly like degree 3 is no good, because if I have any vertex like that, like, if I go through it, I'm going to have 1 edge left that I can never visit. 1 is obviously no good either, because then I'm definitely just going to get stuck. But like, how do we know that degree 5 would be not a thing?
Because if it passes through it, is again taking away 2 degrees of it that can be used to edges on it.
Right.
And then you'll be left with essentially a degree 3 afterwards.
Right.
We notice that.
Right. Yeah, that's right. Every single time that we, if it's going to work, then if I look at any particular vertex, the path that I follow has to go through the vertex possibly multiple times. And every time it goes through there, it's going to use up 2 edges, right? Because I can't get stuck. I need the path to continue, to be a continuous loop. Anything odd is not going to work because the path won't be able to go through continuously every time. I would have like 1 edge left over, no matter how I do it. Okay, so our conjecture, or it's not even, I don't even know if I would say it's a conjecture. We've kind of just convinced ourselves that this is true. So we could say theorem, right? If a graph has any odd degree vertices, it does not have an Eulerian circuit. Or we could phrase it contrapositively and say, if a graph has an Eulerian circuit, then every vertex has an even degree. If G has an Eulerian circuit, every vertex has I really should put like, these are logically equivalent, right? Okay, so let's look at this graph here on the right. Are there any vertices with an odd degree? So, since no one has found any yet, yeah, Adam.
I think there's at least 2 near the bottom of that shape, like near like a trapezoid hole.
Like these ones here, or these ones?
And now yeah,
These ones on the sides, I think, have degree 4.
oh, okay.
All right, 1, 2, 3, 4.
Right, yeah. I think one of the lines might be with the.
Yeah, that's okay.
paper.
Yeah, I know, right. It's a little hard to count sometimes. Okay. Yeah, so I definitely intentionally constructed this graph so that every vertex has an even degree. It's possible that I messed up, which is why I was asking, but I think every vertex has an even degree.
What about that one?
Which one?
Go up further than left hand.
Here?
Yeah.
That has degree 4. Yeah. Fortunately, computers can do this for us, right? We don't have to actually sit there and stare at graphs in real life, but yeah. Okay.
No outside.
Okay. And this one has degree, this one up here has degree 6, actually. Yeah, okay. So every vertex in this graph has an even degree. Based on what we've talked about so far, does that guarantee that it has an Eulerian circuit. See some yeses, some no's. So we definitely know that if there were any odd vertices, then it would not have an Eulerian circuit. And all the graphs we've tried so far that had only even degrees, like this one on the left, like that had all even degrees and it did have an Eulerian circuit. But yeah, I think we have not actually, like, we don't have any particular reason to know. We might suspect perhaps, but we don't know that every graph with all even vertices has an Eulerian circuit. However, it turns out to be true. So this actually is an if and only if, not just an if. So I want to show you how to prove that. So I claim this graph on the right does in fact have an Eulerian circuit, even though it might not be obvious how we would find one. So theorem. Oops. And this, so I told you that, like, Euler wrote this paper in 1736. So actually, so Euler's 1736 paper, he, defined all this stuff about graphs in general, and he actually only proved he proved this direction of this theorem. It only proved, that an Eulerian, well, he didn't call them Eulerian circuits. That would have been kind of full of himself, but other people called it that. He proved that if there is an Eulerian circuit, then all the degrees are even. Right? Or, contrapositively, that if there's any odd, then it can't have an Eulerian circuit. And that was enough because he was just solving that problem, and he said, look, this town, actually it's not on this document. The town looked like this. It was like the graph of the town. So actually, like, I think all four vertices are odd. And he's like, yep, there's no way to do it. That was enough to solve that problem. It's certainly possible that he believed or / knew that it was an if and only if, and maybe he just thought it was obvious and he didn't bother writing down a proof. Who knows? In any case, the other direction of this if and only if, anyone want to guess what year it was first formally proved, like someone published a proof of the opposite direction? Well, maybe we'll play like closest without going over. So anyone want to guess the year? 2020, okay. 2012, okay, sorry. 2012. 2012. Any other guesses out?
1950.
1950. 1980. Garrett.
1937.
1737.
I meant the 17 for sure.
Wait, what?
I misspoke. I meant to say like 1 year after the paper.
Oh, 1737.
Yeah.
Okay. Any other guesses? So I guess Garrett wins because the answer is actually 1871. Although 1950 is closer to 1871 than 1737 is. So if we're just playing by closest, anyway. I mean, whatever. In any case, the point is, it's kind of remarkable that it took like 150 years basically before someone proved this. I don't think it was necessarily because it was all that difficult. It was just like no one cared, maybe, or just people kind of assumed that Euler had proved it, and then they're like, no, actually, kind of sad. This is like one of the very few things that this guy published, because he died when he was very young. And this paper was actually published after he died. Like he had written it up and not actually published it. So one of his friends took it and like got it published after he died. He probably would have done a bunch more stuff if he had not died. I don't remember how old he was when he died, but it was like in his 20s or something. Anyway, in other words, the theorem is, let G be a connected, undirected graph, and then G has an Eulerian circuit if and only if every vertex has even degree. Let's talk about the proof. And this proof is interesting because, so there's in one direction we're actually going to give an algorithm, basically. In this direction, like if G has an Eulerian circuit, then every vertex has even degree. We basically already kind of proved this to ourselves, right? Because if any vertex had an odd degree, you would get stuck there and you wouldn't be able to make it. So we'll just say already proved by us / Euler. The other direction, this is one of those things that says, okay, if every vertex has an even degree, then there must be an Eulerian circuit. You could imagine proving this in a way that just said, well, an Eulerian circuit must exist because otherwise something bad would happen. But we're going to do better than that. We're going to give an actual algorithm that says, yes, one must exist, and here is how you can actually find one. And because this algorithm always works, you can always find one, therefore it exists. But it's actually practical. So like, going back to here, we could construct a graph like this for much larger numbers of bits, and the graph is going to get very large pretty quickly. If we did it for 4 bits or 5, like here we had 4 vertices and 8 edges, but in general, if we did like the next level up would have 8 vertices and 16 edges, then we'd have like 16 vertices and 32 edges. It gets bigger, and it might be hard to just stare at it and figure out what would be a path, but this proof is going to give us an algorithm that we could use to find one. Well, with the caveat that we're only talking about undirected graphs, and that graph is directed, but it turns out you can generalize this all to work for directed graphs as well. All right, let's see how this is going to work. So this is called Hierholzer's algorithm. And it's by induction on the number of edges. Okay, so the base case, if there's 0 edges, well, if you have a graph where every vertex has an even degree, and it has 0 edges, then it must also have 0 vertices. Because there can't be one vertex, because then it would have degree, oh no, that would be okay. Right, it would have degree 0, so that would be even. Yeah. I guess, yeah, then, or since all vertices have even degree, right, G could look like, okay, but G also has to be connected, right? I'll say and G is connected. Right, it must be either empty or vertex would be okay. But, you know, well then, does a single vertex have an Eulerian circuit? Sure. You just sit there. And you have visited all the edges by doing nothing. So, check. Okay, so now, and actually this is going to be a proof by strong induction. We'll see why in a second. So now, let G be an arbitrary graph, arbitrary, let's say connected graph with all even vertices. Right, and we're going to suppose that every graph with fewer edges that that is like this will have an Eulerian pattern. So suppose every graph, every connected even graph. I'm going to start using the word even just to mean all vertices are even. So I don't have to keep repeating the phrase all vertices are even. I'll just say the graph is even. So every connected even graph with fewer edges has an Eulerian circuit. That's our induction hypothesis. Okay? Here's what we're going to do. Pick a random point and just start walking. But don't ever go back on an edge that don't ever visit an edge you've already visited before. Okay? So you're a vertex, you follow an edge, follow another edge, follow another edge. Just make sure if you ever get to a vertex you've been before, that's fine, but just make sure that you don't go along an edge that you've already used before. Okay? I claim that you cannot possibly get stuck until you get back to the vertex where you started. And you definitely will get back to the vertex where you started eventually. Why is that? Well, because all the vertices are even, like any vertex I go into has an even number of edges, so it's got to have at least one more waiting for me to exit from, right? And then I use up 2, so it still has an even number left. So every vertex I go into, there's always going to be a way out, except that vertex where I started, I used one edge going out of it, so it's now got an odd number. And so eventually I could, the only place I could possibly get stuck is if I come back to that vertex. Anywhere else, I'm going to be able to keep going. And so let me write this down. So start at any vertex and keep following edges, but don't reuse edges. You can never get stuck since every vertex has even degree, except you could get stuck at the starting vertex. Okay. However, we're not done, because why is that? Well, let's look up here at this example graph, right? I could start here and say, I'm going to walk, I'm going to go this way, 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 I'm going to go this way now, this way, let's see, there has to be an exit here, and then here, and then here, and now I'm stuck, right? The problem is that I didn't end up visiting every edge in the graph, right? So this can definitely happen. I'll definitely get back to where I started, but it's quite possible that I did not actually end up visiting every edge in the graph. So what do we do? So we will here's the scenario. So here's my like starting vertex, and I went on this path that went around the graph, and I got back to where I started. But there might be some edges I didn't visit. So if I imagine like taking all the vertices and edges that I visited and just like deleting them, right? What's going to be left? I could have multiple pieces left, okay? But since the graph is connected, all those pieces are going to have at least one vertex that they share with the part that I deleted, because, so like there could be some big chunk over here. We'll call this like H1. There could be another thing over here like H2. Right. And this isn't supposed to represent like a path around the outside. It's just a big blob of vertices and edges, right? But it's got to share something with the path that I made. Well, here's the thing. All these pieces are, they're connected. All the vertices have an even degree because like I just deleted, two edges from one of them. And they have a fewer number of edges because I deleted some edges, on my cycle. So by the induction hypothesis, they all have an Eulerian circuit. So let's say, so if we delete the circuit we made, the leftover parts must be connected to our circuit. And then I'll say each leftover part is connected and even and has fewer edges than we started with, fewer edges than our whole graph G. Right? So by the induction hypothesis, each one has an Eulerian circuit. Okay, so that means like, in H2, for example, there's some path that goes around and visits all the edges in H2 and then comes back. Yeah, Grace.
Okay, so I know we're talking about this for like that specific example above, but if it completes a circuit and it leaves a part out, will it still be able to like complete does that mean it's like definitely completes the Euler circuit? Like always?
Well, which?
Like if you scroll up a little,
yeah.
like looking at our shapes,
Uh-huh.
like let's say there was another shape that was like this, but maybe it doesn't complete the Euler circuit or whatever.
Right.
Would it still be able to maybe complete the circuit like somehow with leaving some parts out, or is that not possible? You know what I mean? Like, you know how you're talking about, oh, maybe it's completed the circuit, but it's left a
Right.
large chunk out.
Yeah, yeah. So the chunks that are left out in this example, so there's there's like this whole piece that's left out, and then there's like, this whole piece that's left out.
My point is, would it be able to work like that with maybe a shape that doesn't complete the Euler circuit? Like this shape, this does with the Euler circuit.
Well, no, I mean, I'm just in the middle of proving that we will be able to always complete the entire circuit. Do you mean like where the leftover shape doesn't have an Euler circuit itself? Or do you mean where we can't like complete it to actually make a circuit of the entire graph?
I'm just asking if it's like, if we would ever be able to create, like, we have this like really large example here, and obviously if I remove like one edge off this, it could like, you know what I mean, that completes the circuit.
Right.
Would I still be able to find a way to like get like a part of it, you know what I mean?
Right.
To get that circuit.
I mean,
without the whole thing being able to like be that.
I mean, so maybe you're saying like if I somehow like find kind of the biggest possible circuit that will still include as much stuff as possible, even though there's like a little bit that has to be left out? That's a really interesting question, and I don't know the answer. I mean, certainly there is some like biggest possible circuit that exists that you could. I don't know how hard it is to find.
Every shape that we know has an Eulerian circuit, have a unique one, or is that more?
No, no, definitely not. I mean, I can show you a very simple example. Let's see. Let's see. Okay, what was it? I mean, here, like, I have a choice. I have to go around each triangle, but like which order I go around them, I have some choice there, right? And if you label the vertices, like it's different. You know, if I go around this one first, and then this one, and then this one, that's different than like going around this one, then this one, and this one. I don't know. And like, I mean, even this one, if you think about, if you try some other things, like, because I had a lot of arbitrary choices that I made when I was wandering around first, right? I could have made different choices, and the point is, it doesn't matter. It's always gonna lead to some Eulerian circuit. So, in general, a graph could have lots of them. Okay. So going back to this, right? The point is, by the induction hypothesis, each one of these pieces has, you know, some Eulerian circuit itself. And I claim I can now put these together to make an Eulerian circuit, the whole thing. How do I do that? Well, I start where I started. I follow the path that I was following before. But when I get to one of these shared vertices, I kind of pause, and I just like go around this whole circuit, and then I come back to here, and then I continue on my way, right? I go along here, and I come to here, so I'm going to go around this one, and then I come back to here, and I continue, right? And I'm going to end up going around the entire thing, and visit every single edge. So it's kind of like, well, we didn't quite make the right choices when we were wandering around at first, but we can fix it by like figuring out how to go around the missing parts and then kind of splicing those parts in. Saying like, oh, right here, pause, don't go that way, just splice this in, get all these first, and now you can keep going. And that will always work. Just say, and we can splice them into our original circuit to get an Eulerian circuit of the entire graph. So let's, for the last 2 minutes, let's try it on this graph. So I'll use a different color here. Well, okay, like this part that was left here, I already have this pink part is in fact an Eulerian circuit for that piece. And then down here, you know, again, I do the same algorithm. I'm like, okay, well, let's start here. I'm going to wander, like I'm just kind of going around the I can't use that edge. I already used that edge. Okay, so actually I got lucky, and I wandered randomly, and I ended up in fact hitting every edge. If I hadn't gotten lucky, it's possible that the same thing would happen, and I would get stuck again, and there would be another piece. But I just keep doing the same thing recursively. I say, oh, fine, let's go do that piece, and then splice that into here, and then I splice the spliced thing into the right, because that's, you know, a proof by induction kind of corresponds to a recursive algorithm. So the induction hypothesis said, well, these parts that are left over definitely have one. Well, how does that work? Well, it's the same proof. Right? So we can finally put the whole thing together into right. So I don't know. I like started here. It's like, and then when I get actually. When I got to here, right, that's a vertex that's shared with this pink thing. So I can go around this cycle with you next week, so definitely sign up for help on modules and whatnot. And,